Hi, this is a second video on data sufficiency. The topic is number theory. So as usual, I expect you to first solve the worksheet given in the description of this video. Yeah, and then come to this video for explanations. So I'll begin with the explanations now. First question. If x and y are positive integers, then what is the least common multiple of x and y? Okay. Okay, it says x is twice y. Right. So assuming y is 8, x is 16. So the least common multiple of x and y is 16, right? Okay. But then if you take y as 3, then x is 9, and the least common multiple is 9. So we don't have a definite answer. So A is not sufficient, correct? And D is out. Either x or y is a prime number, but not both. So let's say y is the prime number, correct? So you get x as 9. Yeah. But if x is a prime number, now x could be a prime number only when x is 2, correct? And y is 1. Okay. So this is, of course, yeah. All right. So x or y the prime number, but not both. So on its own, right, it doesn't tell us anything. But when we take both the situations together, then we can take this as an example where y is prime and take this as an example where x is prime, correct? And we are also satisfying statement A. Even then, we get two possible outcomes for the least common multiple of x and y. One is 9 and one is 2. Therefore, C is also out. E is the answer. Okay. Now, out here in this question, had they said that only x is a prime number, then we would have had a definite answer. Because x being a prime number and x is twice of y, taking these situations together, or even the statement x is a prime number. So yeah, so we would have to take both statements together if they had mentioned only x is a prime number. So had they just mentioned in statement B that x is a prime number, then there's only one possible outcome, because when x is twice y, it means it is 2 times, and meaning it becomes an even number, and we know that 2 is the only even prime number. So there will only be one possible answer. C would be the answer in that situation. But I did not design it that way. All right, moving on. Second question. If x is a positive integer, then how many positive factors does x have? X is equal to a prime number raised to the power 16. All right. So in number theory, yeah, x is equal to a prime number raised to the power of 16. This is what they're saying. Okay. So in number theory, suppose you have 8, and 8 is a prime number raised to the power 3. All right. Once we know this part, right, prime number raised to 3, then 1 more than 3, that is 4, 4 factors. And it clearly states how many positive factors. So this technique gives us 4 factors. You just raise 1 more than the power of 3. Okay. And I can show it to you. Factors 1, 2, 4, and 8. 4 factors of 8, positive factors. There could be 4 negative also, -1, -2, -4, and -8, but we are only looking at positive factors, right? So A alone, yeah, or A on its own gives out the answer the moment we come to know, yeah, that x is equal to a prime number raised to the power 16. So we know that there'll be 17 factors, yeah, x has. Are you with me? And just an extra explanation. Suppose the number was 18, yeah, or 36. Let's make it 36. Then 36, yeah, is 2 to the power 2 into 3 to the power 2, correct? 2 square into 3 square. So then how do we find out the number of factors, positive factors? So 1 more than 2 is 3. 1 more than 2 is 3, and you multiply them. You don't add them up, you multiply them. And you come to know there are 9 positive factors of 36. So those are 1, 2, 3, 4, 6, 9, 12, 18, 36. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it? So this was just an explanation of the technique out here. So the idea of giving you this worksheet is to obviously draw out the concepts of number theory and to solve these questions. Okay, so we know that A answers. And because A answers, B and C is out, E is also out. Okay, so it's either A or D. Yeah. Let's look at the second statement. If x is raised to the power of 2, so if x is raised to the power of 2, not a prime number, right? If x is raised to the power of 2, then it would have 1 less than twice the number of positive factors, 1 less than twice the number of positive factors it would have had when not raised to the power of 2. Okay. Now, this statement is quite confusing to begin with because this statement is probably already assuming that x is equal to a prime number something. So let's just take an example for x. Okay, so we know x is a positive integer. Let the value of x be 4, right? So when x is raised to the power of 2, right? So when x is 4 square, 16, right, which is 2 to the power of 4, it would have 1 less than twice the number of positive factors it would have had when not raised to the power of 2. So this statement is incorrect actually. It should have been when x would have 1 less than twice the number of positive factors it would have had when raised to the power when x is raised to the power of 2. So it should be the other way around. So let me read the statement again anyway. If x is raised to the power 2, then it would have 1 less than twice the number of positive factors it would have had when not raised to the power of 2. No, the statement is correct. It just means that if x is raised to the power of 2, that is, if x is 4 and x is squared, that is 16, 2 to the power 4, then it would have, so it would have 5 factors according to this concept, right? Yeah. So that is 16. 16 would have had 1, 2, 4, 8, and 16, 5 factors. So it would have 5 factors. So it would have 1 less than twice the number of positive factors, yeah, it would have had when raised to the power of 2, when not raised to the power of 2. So when not raised to the power of 2, it would just remain 4. And with 4, it is 2 square. And with that, it would have 3 factors, right? So it would have had 1 less than twice the number of positive factors, 1 less than twice the number of positive factors. So into 2, 6, right? Into 2, 6 minus 1, 5. 1 less than twice the number of positive factors it would have had, right? When not raised to the power of 2. So basically, it just depends on the x value you take. So right now the answer is 5, right? Or probably you come to know that it would have 3. Okay. How many positive factors does x have? Not x squared. So it would have 3. So if I take x is equal to 9, yeah. So in that case, x would be having 3 square. So it would be having 5 factors, right? it would be having three factors. It would be having three factors, and x square would be 81, and that is 3 to the power 4. It would be having five factors. So even then, the answer would have been 3 and 5. But if you take some other number, like let's say 16, then it is 2 to the power 4. And in that case, it would be 5. And 16 squared is 256. It's 2 to the power 8. Yeah. In that case, it would be having, yeah, 9 factors. So the answer would change from 3 to 5. You know what I mean? So second statement doesn't answer the question. Leave out A is the answer. Okay. All right. So I realized that it was all too cramped up. So I'll resolve the second statement again for you. All right. So in the second statement out here, if x is 4, yeah, then it is 2 square. In that case, according to that concept, there will be three factors, 1, 2, and 4. Correct? Now, if x is raised to the power 2, meaning x square, meaning 4 square, meaning 16, meaning 2 to the power 4, then it would have five factors. Correct? And that's what they're saying. If x is raised to the power 2, then it would have one less than twice the number of positive factors it would have had when not raised to power 2. So one less than twice of 6, twice of 3. So that would be 5, basically. Are you getting it? Now, I took an example which was x is equal to 3 and I got the same outcome. So I took x as 16. Right, with 16, I got 2 to the power 4 and I got five factors 1, 2, 4, 8, and 16. Right, and therefore x square would be 256, which is 2 to the power 8. Are you with me? Yeah, which is 9. Right, 1 less than twice of 5, which is 9. So in that case, I'm getting two possible answers for the factors of x, and there could be even more than two possible. Right now, it's two possible depending on the examples I took. So the answer would be 3 or 5, depending on what the value of x you take. Are you getting it? Therefore, when this, and this was gone, and A and D left, and we looked at statement B got out. So D is out because statement B is not giving us a definite answer. Are you getting it? Whereas A gives us. Just to explain A again, yeah, the concept is that whenever you have any particular number that you take, so for example, suppose you took, let's say 25. Okay. So suppose you took 25 and 25 is 5 square. So it is a prime number raised to 2. It will have three factors, one more than the power. It'll have three factors, 1, 5, and 25. Are you with me? So when they say that when x is equal to a prime number raised to the power 16, so we already know the answer is 17 factors, one more than 16. We don't care about what the number is. The question is how many positive factors it will have. All right. And the reason I asked particularly positive factors because 25 has how many factors? It has six factors, three positive and three negative. Are you getting it? Six factors, but then we are only looking at positive factors, and this technique gives us only positive factors answer. So we'll have to double it if you want to find out how many factors does x have. So would the question work if the question was how many factors does x have? Yes, it would have worked. But positive factors makes it more, specific to this technique out here. Anyway, let's move on to the third question. If x and y are positive integers, then is x to the y an odd number? Is x to the y odd? Yeah. So first statement, x is a prime number. So we know that the only even prime number is 2, right? And 2 to any positive factor you take will be an even number. But rest of the prime numbers are odd. So 2 to the power any number you take y, the outcome will be odd. So the first statement gives us two possibilities, even and odd. right? For x to the power y. Second statement, the product of x and y is even. All right. The product of x and y is even. So the product of x and y is even. That means x could be, again, see out here, suppose we ignore this part, yeah, right? So we can take 2 to the power 3, right, and 2 to the power x, and the product of x and y is even, 2 to the power 2, and we can take 3 square. All right. So out here the outcome is 8. Out here the outcome is 4. Out here the outcome is 9. So with the second statement on its own, is x to the power y odd? Now x and y could be any two positive integers. So I've taken trial and error. I've taken 3 examples out here. Yeah. And I found out that, is it odd? No. No. And out here, yes. So we are getting two answers, no and yes also. So first statement is, second statement is also not sufficient, right? Yeah. So now we take both statements together. When we take both statements together, we have to take x as a prime number, right? So when we take x as a prime number, correct? So I've taken x as prime number here, x as prime number here, x as prime number here. All right. Yeah. And also I have to make sure that product of x and y is even. So out here, yeah, I've made sure that x and y is even. Yeah. The product of 2, 3, 2, 2, and 3, 2, they are all even. Like 2 into 3 is 6, 2 into 4, and 3 into 2 is 6, right? So again, we're getting a no yes answer. So taking both together also, we're not getting a definite answer. Hence the answer is E. Okay. Then is x to the power y an odd number? Correct? Mhm. Okay. Right. Moving on. Fourth question. Right. If x and y are positive integers, then what is the unit digit of their product? X is a multiple of 5. So we can take 5 also, or we can take 25. So we'll take both 5 and 25. Okay. So x is a multiple of 5, doesn't tell us anything about y. So A, B, C, D. We know A doesn't answer, D doesn't answer. Okay. Now statement B, y is an even multiple of 7. Y is an even multiple of 7. So can we take 7? No. Can we take 14? Yes. Can we take 21? No. Can we take 28? Yes. Correct. So I've taken 2 examples for x and 2 examples of y. Now, y alone, B statement alone also doesn't answer the question. What is the unit digit of the product? So B is also out. Now, both together or E. All right. Those are the only two possibilities. So when we take both together, we have taken examples of x, examples of y. So we'll take 5 with 14. We know that it is 70. 5 with 28. We know it will be 140. Yeah. So what is the units digit of the product? 0 and 0. Correct. Are you with me? Right. Now we'll take 25 and 14, and we know that it will end with 0, and 25 and 28, we know it will end with 0. Correct. Because 25 and 14, we look at the last two numbers, 5 and 4, so it becomes 0. And same with 5 and 8, 40, 0 comes in the end. So together, we are getting a definite answer for this one, C. Correct. Yeah, that the units digit of the product is always 0. Are you with me? Yeah. So out here, C is the answer, E is out. Okay. That was easy. The confusion would have appeared, come about had you misread the B statement that y is an even multiple of 7. Okay. Because even goes out, then there are two possible outcomes. We can try it out. Let's move on to question 5. Okay. X and y are positive integers, then what is the highest common factor of x and y? Okay. So first statement. 1 is the only other factor common to x and y. Only other common factor to x and y. Okay. Does it answer the question? No, because it says there are two common factors out here. With statement A, we come to know there are two common factors, one and something else. So to give you an example, let's take 5 and 25. The factors of 25 are 1, 5, and 25. Factors of 5 is 1 and 5. So the common factors are 1 and 5. Are you with me? And out here, we can say that one is the only one is the only other factor common to x and y. So let's take this x and this is y. Are you with me? So we can say, what is the highest common factor? The highest common factor is 5 out here. But if we took the numbers 7 and 49, then we get 1, 7, and 49, and we get 1 and 7. And out here also, we know that 1 is the only other factor common to x and y. The only other factor common to x and y. In such situations, the highest common factor could be 5 also, 7 also. It's a trial and error situation. So A is out, D is out. We look at statement B. X is the prime number. So when x is the prime number, I think we took x as prime number out here. Correct? Both we took. Correct? Yeah. So, but with sexy, with the second statement, x being a prime number, we don't have y to be work with. So B is out. Okay. So when we take both together, we can use the same examples that I've taken where x is a prime number. And yet, if you see, I'm not getting a definite answer. Correct? Yeah. Even when x is a prime number, I'm not getting a definite answer because, yeah, I've taken examples to show you. So C is out, E is the only outcome out here. Understood? Yeah. Question 6. Remember, those who are new to my channel or this video, complete review in detail of the subject of the topic, number theory is given in some other channel. Description is given in the video out here of that channel. Okay. Yeah. This channel out here will only do, will only work for advanced learners who already know their number theory topic properly. Yeah. Okay. Moving on to question number 6. X and y are positive integers, then what is the remainder when x is divided by y? So statement A, B, C, D, E, like that. Statement A, x is a multiple of y. So when x is a multiple of y and x and y are positive integers, then clearly x is a multiple of another integer. Therefore, x is also an integer, right? I mean, x is a multiple of y, right? So when x is a multiple of y, then the remainder when x is divided by y is always going to be 0. Like for example, 16 is a multiple of 8. So 8 and 16, 8 to the 16, the remainder is 0. Correct? So A answers, right? A answers, then B, C, and E is gone. It's either A or D. Correct? Statement 2. When x is divided by y, the result is an integer. So when x is divided by y, the result will always be an integer, right? So when you always have an integer, that is the quotient is clear cut out here, then you know that it will give you a remainder. When x is divided by y, the result is an integer. Now, had it had a remainder, for example, if you take 8 and 17, 8 twos are 16, and you get remainder 1. Are you getting it? So in this situation, you probably, if you want to finish off the question, then you'll get 8 ones are 8, you get remainder 20, 8 twos are 16, remainder 40, and 5. So it will be 2.125. So you know that when x is divided by y results in a non-integer number, then you know that it would definitely give you some kind of a remainder. But if it's an integer, right, then you know that the remainder will always be 0. Therefore, B also answers. D is the answer. Got it, guys? Okay. So D, seventh question. If x and y are positive integers, is the product of x and y a multiple of 385? All right. So 385, 170, and 600 is 770, right? So these are the multiples of 385. So is the product of x and y a multiple of 385? So statement A, B, C, D. Statement A, x is a multiple of 7 and y is the multiple of 11. So see, we can take x as 7 also, and 14 also, correct? Yeah. And we can take y as 11 also and 55 also, you know what I mean? Yeah, correct. Okay. And we can take it as 22 also. 55 I took because I see a 5 ending, so I know something to do with 5 is also there, right? 5 also. All right. So is the product of x and y a multiple of 385? So we'll take x and y 77, right? 7 is the multiple of 7, 11 is the multiple of 11. So I can take 7 into 11, 77. Is 77 a multiple of 385? No. Okay. Now let's take 14 and 55. Yeah. All right. So what is 14 and 55? 14 5 are 70. 14 5 are 70, 77. So is x and y a multiple of 385? Yes. So first statement gives you a no yes situation. A is out, D is out. So it's either B, C, or E. Okay. Right. Second question. Second statement. The least common multiple of x and y when multiplied by the highest common factor of x and y gives a result equal to a multiple of 385. Now this is a concept, number theory property. All right. Yeah. If the least common multiple of x and y multiplied with the highest common factor of x and y gives the result equal to 385 or equal to a multiple of 385, which would be 385 itself and all multiple of 385, right? Then we know that the product x and y is a multiple of 385. How? So it's based on a property, like for example, suppose you took, yeah, I'll give you a small example. Suppose you took 4 and 9. Let's say this is x and y. So what is the least common multiple of x and y? So we start with the highest number, 9 to the 18, 9 3 the 27, 9 4 the 36. So 36 is the LCM. Now what is the highest common factor? So the only common factor out here is 1. So 1 is the HCF. And if you multiply these two, 36 and 1, you end up getting the product of x and y. Are you getting the picture? So the property is such that product of two numbers, I'll write it down in a text form. Product of any two integers outside is always equal to the product of any two integers is always equal to the product of its HCF and LCF. Okay, simple.
Product of any two integers is always equal to the product of its HCF and LCM. So second statement is basically, iterating that in a different way. It is stating that it's a multiple of 385. So we know that the least count multiple of x and y when multiplied with the highest count factor of x and y gives a result equal to a multiple of 385. That result is nothing but the product of the two numbers x and y. Are you getting the picture? So the product of x and y, is it a multiple of 385? It's directly answering the question that it is a multiple of 385. Is the product of x and y multiple of 385? Yes. So B statement answers the question. Yeah, C is out, E is out. B is the answer. Yeah. Okay. Question A.
If P and Q are positive integers, then is 2 to the power P a factor of Q? In other words, is Q a multiple of 2 to the power P? Okay. So A, B, C, D. Q is a product of odd numbers between 1 and 30. So Q is equal to odd numbers between 1 and 30. So it will be 3. Yeah. Not 1 because it says between. So we can't include 1 and 30. So 3 and 5 and 7 and 9 and so on. So is 2 to the power P a factor of Q? So product of odd numbers is going to be an odd number. Q is the product of odd numbers. So odd numbers when multiplied will give you an odd number. So we know this is an odd number. An odd number will never have an even factor. Think of it, 27, 29, 31, 33. Yeah, these two are primes, obviously. So if you took at 27, it is 1, 3, 9, and 27. These are the factors. No even number. 33, 1, 3, 11. No even number, right? Yeah. So obviously we can't take 31 also and 33 also because it says between 1 and 30. So we take 19, 1 and 19. No even number. We take 23, a prime number again, unfortunately, right? We'll take 25, chalo. 1, 5, and 25. No prime, no even factor. So even factor 2 to the power something will be an even number. So the answer is no, a definite no. So does A answer the question? The question is then is 2 to the power P a factor of Q? It's a definite no. So when it's a definite no, B, C, and E is out. It's either D or A because A answers. Now we look at the second statement. P is an odd number, right? P is an odd number doesn't tell us anything. It just tells us that 2 to the power something which is an odd number, like 3, like 2 to the power 5. It just tells us that this is outcome is even. Outcome is even. Outcome is going to be even anyways, whether P is odd or not. Are you with me? So B statement doesn't answer the question. Therefore, D is out. Only A answers. Got it, guys? Yeah. Statement B doesn't tell us anything. Okay. It doesn't tell us anything about Q. So only A answers. Okay. Question 9. Out of X marbles, 12 friends each get Y marbles with J marbles left unshared. So X is equal to 12Y plus J. That's what it means. Okay. 12 friends each get Y marbles, so 12 into Y, with J marbles left unshared, meaning J is a remainder. X is equal to 12Y plus J. All right. Yeah. Okay. So just to get you a grip on this equation, suppose you have 25 and 2 into 12, or 12 into 2. Let's put it 12 into 2. All right. So imagine X is 25, 12 friends is 12, each getting Y marbles. So Y is 2. Are you getting it? J is unshared. Okay. Anyway, so you can ignore this example just for your understanding. If 5 friends leave, right? So then there are 7 people remaining. Then all of the X marbles are equally shared amongst remaining friends with no marbles left over. So simply saying, yeah, right. Then X is X upon 7, basically. So basically it says that X is a multiple of 7. Are you getting the picture? Yeah. With no marbles left unshared. X is a multiple 7, X is equal to 7y. Or you can say even better, X upon 7 gives you an integer value. Okay. Yeah. Correct. So what is the value of X? Hmm. Okay. Statement 1, A, B, C, D, E. If Y is 4, so we'll go with this and statement 1. If Y is 4, then the marbles unshared is equal to 5 times the number of marbles unshared when Y is 5. If Y is 4, then the marbles unshared is equal to 5 times the number of marbles unshared when Y is 5. So this is what it is. Another complicated statement to, you know, translate English to algebra, to be honest. It's just forming an expression. So we know that X is 12y plus j, where j is unshared. So it says that when Y is 4, the number of marbles, the marbles unshared, that is j, is equal to 5 times the number of marbles unshared when Y is 5. So suppose when Y is 5, yes, and the number of marbles unshared is j, right? Then when Y is 4, the marbles unshared is equal to 5 times j. That's what it simply means. This is the statement. It's equal to 5 times the number of marbles unshared when Y is 5. Are you getting the picture? X is 12 times 4 plus 5j. So we can simply equate these two expressions. 48 plus 5j is equal to 60 plus j. So we get 4j is equal to 12, j is equal to 3. Yeah. With j3, we can plug in anywhere and get our answer. Right. So what is the value of x? Right. So when j is 3, yeah, we get 63. And out here we get 48 plus 5 times 3, 15. Yeah, which is also 63. Yeah, both gives us exactly same value of x, which is 63. So what is the value of x? A gives us the answer. A gives us the answer. Then A or D is the possible outcome, right? So I think uh, with statement B, x is a multiple of 7. Yeah, it could be 27. It could be 63. Yeah, multiple of 7. Sorry, 27 is not multiple of 27. 42 or 63. Yeah. So x is a multiple of 7 doesn't tell us anything on its own. So only A answers, B doesn't answer. Therefore, D is out. A is the answer. Okay. Right. Okay. Hang on. Right. 10th one. When Jane squared each integer presented to her, she found that the numbers did not end with 3, 7, and x. What is the value of x? So even before we look at statement A and B, this is a cyclicity concept. Okay. So this concept I've tried and explained in the full review of math under a different channel. All right. So go through that. Right now, all I can say is that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Now, I'm not saying these are the integers presented to her. I'm just saying that, yeah, any of these integers, when you square them, yeah, you'll end up getting a result ending with 0, 1, 4, 9, 6, 5. 4 squared is 16, so 6. Are you getting it? 6 squared is 36, so the ending, the result will end with 6, 9, 4, 8 squared is 64, and this. So what you realize is that 0 is ending with, 1 is ending with, it's not ending with 2, right? It's not ending with 3, it's not ending with 7, it's not ending with 8, right? But it's ending with all the other digits. So out here, it says it does not end with 3, 7, 3, 7, and x, where x could be 2 also and 8 also. So that is, if you know this cyclicity concept, then you know which direction to go in. Otherwise, math number theory is an infinite. There are infinite theories and concepts under number theory. All right, yeah. So you'll be lost, and when you're lost, you'll end up doing a lot of trial and error and yet get the question wrong. So knowing the cyclicity concept, you know whether question is taking you towards which topic it's taking you within math. Yeah, so it's taking you towards a cyclicity number theory concept. So okay, so now we need to find out x. Now we know that x is either 2 or 8. Okay, it narrows down to this concept. So statement A, B, C, D, E. When Jane squared all integers from 0 to 9, she found that the results did not end with 2, 3, 7, and 8. All right. Yeah. So we already know this statement A part, right? We already know that. If you know the number theory concept of cyclicity, then you already know that 0 to 9 when squared will not end with 2, 3, 7, and 8. So the statement A is not really helping you. It's something which is just stating this is the case. All right. We already know. Yeah. Anyway. B. If Jane cubed one of the integers presented to her, right? See, when Jane squared each integer presented to her, when Jane squared all integers, see that the difference between each integer presented to her and when Jane squared all integers. Are you getting the picture? Any which way, all right. If Jane cubed one of the integers presented to her, right, then the result would be equal to the cube of x. Yeah. So when Jane cubed one of the integers presented to her, all right, the result is equal to cube of x. Then that integer is x itself, right? That integer is x itself, right? All right. So what I'm trying to say is that x cube, cube of x, is equal to that integer cube. I'm using it I as an integer cube, which is equal to the same number, right? Yeah. And we know that it will not end with 2, 3, 7, or 8, where out here x could be either 2 or 8. Correct? Yeah. So the question is, out here you need to understand this question carefully. That statement B, it tells us that it is a cube of x. When Jane cube one of the integers presented to her, then the result would be equal to the cube of x. Right? That means the integer that is presented to her, right, is 2 cube, okay, or 8 cube, right? When Jane cube one of the integers presented to her, then the result would be equal to the cube of x. Out here in statement 2, there's nothing to do with the last, the outcome of the last digit or the ending with. Okay, out here it's simply stating that when Jane cube one of the integers presented to her, yeah, the result would be equal to the cube of x. All right, so it would be either be 2 cube or cube of x. When Jane cube one of the integers presented to her, then the result would be equal to the cube of x. Had I put the statement as that when Jane cube one of the integers presented to her, then the result would be equal to x, right? Then it would probably give you a definite answer 8 equal to x. So integer when, yeah, it would be equal to, but we don't know that part. So taking the question as it is, if Jane cube one of the integers presented to her, then the result would be equal to the cube of x. Now x we know could be either 2 or 8, so it will be 2 cube or 8 cube. 2 cube gives us 8, correct? And 8 cube gives us, I think, 512. Okay, right. So that also doesn't give us the answer as to what x would be. We don't know that. Okay, so B also doesn't answer the question. We'll take both together. Both together, um, when Jane squared all integers from 0 to 9. So let's assume that the integers presented to her are the same thing as the integers that she squared all integers from 0 to 9. Okay. See, when Jane squared each integer presented to her, she found that the number did not end with 3, 7, and 8 was the value of x. When Jane squared all integers from 0 to 9, okay, so when we take both statements together, statement A, we already know that 2, 3, 7, 2, 3, 7, and 8 is the number that the results will not end with 2, 3, 7, and 8. So we already know that, and we already work with that. So I think if Jane cube one of the integers presented to her, then the result would be equal to the cube of x. That doesn't tell us anything. So in this entire statement out here was there to just mislead you, waste your time, confuse you. There is no answer. There's no way you can get an answer for x. All right. So if you cube one of the integers presented to you, it will be equal to the cube of x. So if I cube 2 cube, yeah, one of the integers presented to you, 2 cube, it would be equal to the cube of x. If Jane cubed one of the integers, if Jane cubed one of the integers presented to her, then the result would be equal to the cube of x. Ah, okay. So now I think we can get somewhere. All right. So I think C will answer the question or A alone. I think when Jane squared each integer presented to her, we don't know which integers she's squaring, right? But A statement tells us which integers she's squaring. So now we get something that with both statements together, we come to know that if Jane cubed one of the integers presented to her, right, and that is obviously 2 cube, right? Because then we know that the result would be equal to the cube of x, right? Cube of either 2 or 8. So the result would be equal to 2 cube. One of x is 2, right? So it will be equal to this. So we know that x is 2 then. Make sense? Because none of these other numbers when cube will be equal to uh, you know, I think if she cubes 8, Okay, hang on a minute. If Jane cubed one of the integers, so if she cubed 8, then it would be 512. It would be the result would be equal to the cube of x. Yeah, again, we are getting two possible outcomes. 2 cube and 8 cube. Are you with me? So yes, answer is E. We are getting two possibilities, right? If Jane cubed one of the integers presented to her, then the result would be equal to the cube of x. So if she cubed 8, yes, then it would be equal to 8 cube. So this is also a possibility. Therefore, we are getting two possible outcomes, 2 or 8 again. So C is also not working. E is the answer. Yeah. I think in my explanation, I was hoping to get B as the answer. I think I kind of was trying to give 2 as the answer, but then out here, I should have made the statement such that it would bring 2 to the only possible outcome, and B would be the only possible answer. And then statement B alone answers. But then, unfortunately, I worked it over and yet found B to be the answer. But then when I am solving it this way, I realize that E is the answer. Okay, that's it. Thank you for your time.